All right. So last class we were discussing block diagram reduction. Okay. So we'll look at an example. We discussed three forms of block diagram reduction: the cascade, parallel, and feedback. Okay. So we'll take a look at an example. We have G1, have summation blocks. You have G2, and G3. Okay. So you'll be given such an example, and you'll be asked to reduce this block to an equivalent block. Okay. The question would be, what is the equivalent block or transfer function? So question would be, what is C of S over R of S? Okay. Now you've learned the three forms of block diagram reduction, right? So you have to employ those three blocks, three types. So the first one you're going to see is this one, right? You can do a cascade on this one. So you're going to have G2, G3. I'm going to omit the S part it's understood that it is G2 of S and G3 of S, okay? And then you have if I do this, H1 of S H2 of S and H3 of S minus, minus, minus. Nothing changes. You see that? You have G1 and here it is. Okay. And this, you can say G1, you have summation block and another summation block G2, G3, and then now you can have here H1 plus H2 plus H3, right? And you have just one negative sign. This positive still remains.
Is that because, based upon what we learned in the last class,
So this, you can think about this, so reverse this, that would be parallel. If you look at the mirror image of this, you can think about this as parallel. Okay, this is the parallel operation. This is the cascade operation. This was the cascade operation. And finally, we employ the feedback operation. So for this, feedback is, so you have G1 you have G2, G3 over 1 plus G2, G3 over into H1 plus H2 plus H3. Okay. This is a feedback. And finally, you have, if you combine this, you're going to have one equivalent block, which is G1, G2, G3 over 1 plus G2, G3 into H1 plus H2 plus H3. Okay. So this has been reduced to this. Okay. This is still a transfer function. It just means that it is a transducer or a sensor. This means it's a plant or process. The G stands for plant or process. This just means it's a sensor or a transducer or some kind of amplifier you can think about. It's essentially a transducer. Okay? And in more often than not, this is a sensor. H of S represents a sensor. The general notation for H of S, you have to understand what this block means. This block means the forward path will have plant, and whatever output is being transduced or sensed. So the sensed output is being changed to something which you can read, which the controller can read or interpret. H of S is again still a transfer function, but it represents a transfer function is for a system, right? It could be any system or a subsystem. A sensor is a system, correct? What is the transfer function? It just defines the input-output relationship, okay, of any system. So this just means it is the input-output relationship of that particular component or a system. Okay. Now, you'll often come across, or you'll find the need to move blocks. Okay. So, for example, if you have something like this, now you see whatever signal you're going to is so what is C of S? C of S is R of S. You have to be able to represent these signals in mathematical form, okay? So C of S is essentially R of S plus or minus X of S into G of S, right? You see it? You see how that is happening? Right? The two signals are being added here, and those both get transduced or go through plant, and this is the output signal. Now, if you want to move this block here, there will be a need for you to move blocks around. So you have to make sure whatever the output signal is the same. So these two are equal, this one and this one. Okay? So you will be often required to do this. For example, even this one, if I had a system here, another system here, you would be required to move this on the other end. At that point, you should use something like this. You will be required to use something like this. So you should understand, you should be able to verify that whatever output, does the output change? C of S, what is C of S here? R of S into G of S, right? plus or minus x of s into g of s. Is it the same? It's the same, right? So the signal is not changing. Okay. So when you do your examples, you'll figure out on page 241 of the textbook, you'll find many other examples or many other ways of moving around blocks, and you should be familiar with those blocks. You will have to be familiar with those blocks. Page 241 in the textbook. Okay. Another example, so you'll be given something like this. This is a very common please familiarize yourselves with this feedback systems, okay? So you'll be given something like this. And the question would be something like, what is the peak time, percentage overshoot, etc. Okay. So you know how to calculate the peak time or the percentage overshoot, right, for this system. For this system, you know how to do it. So when you're given such a system, the first thing you need to do is, here, what do you need? You need G of S equal to C of S over R of S. So what is this? That is just the plant. So here, the closed loop system is generally represented by T of S. We use the notation T of S to represent a closed loop system, okay? So G of S is just the plant. So T of S is, you guys have to stop with your cell phones. Huh? Okay. Don't do that. So what is T of S here? T of S is, you have to always remember this, G of S over 1 plus GS HS, okay? What is H of S? Right, so what is it here? It's just 1, yeah. Right, so, but this becomes 25 over S into S plus 5 over 1 plus 25 over S into S plus 5, okay. So this would be, T of S would be 25 over S square plus 5s plus 25. You need to, these values are for this system. Okay? Always the first thing you need to do is you need to figure out T of S. So the settling time, peak time, percentage overshoot you're required to find is for the closed loop system, and the closed loop system is this. Okay? And you could be, another example would be, let's say, you could be given a simple system like this, K over S into S plus phi. Question will be asked, design or find a value of K for given peak time, percentage overshoot, etc. Okay? Yes? No, not midterm. So midterm is chapter 3 and 4. So you'll be asked to design or find a value of K to achieve these performance characteristics, transient response characteristics. At that point, your first step would be to find T of S. T of S is the closed loop transfer function. T of S will always represent a closed loop transfer function. We will use G of S to represent the open loop. Okay? So here T of S, what is T of S here? What is T of S? This whole thing is T of S. Okay, so we did that, right? We compressed this into one, right? Equivalent block. You need to do that same thing here. So this equivalent block here is what? 25 over S square plus 5S plus 25. So you need to, the T of S is an equivalent block or the closed loop transfer function. So you need to arrive at the equivalent transfer function all the time. And for your lab, what you're going to do is, see, MATLAB is still not capable of reducing blocks for you, right? It cannot reduce the blocks. If you're given a system like this, it will not tell you what the equivalent block is. Especially something for complicated blocks like what we just did. So how do you verify whether you're doing something is correct or not? Right, exactly. So if you want to verify, if you can build such a block. You can even build the complicated block we saw first. in MATLAB. And you can do the simple block. You take those two blocks, and what you do is you plot the step response of both of them. And if these values are the same, you can verify these values, right? If those are the same, it means your block reduction is correct, right? So if you want to verify if this block and this block are the same, is correct, all you need to do is you have this, you build this in Simulink, you take the step response, you specify R of S as a step input, and put this in a scope. So you look at the response of this, you look at the response of this. If the response is the same, it means your block is correct, your block reduction is right. So there is another reduction technique, it's called signal flow graphs. So what we saw was block diagram reduction. The signal flow graphs is another technique for reducing blocks. And here, the components, the basic building blocks, this represents a system, okay, and this represents a signal, okay. This is kind of confusing, but you have to pay attention here. Generally, lines represent signal, right? That's what we saw in block diagram. But here, this represents system, G of S, and this represents a signal, okay? And something like this represents a interconnection of signals and systems, okay. So these are the only components which are used for signal flow graphs. There is no summation block here. You have to pay attention to that. Again, just like block diagram reduction, you have three reduction techniques, or so you have cascade, form, so if you have something like this in block diagram, G1 of S, G2 of S, C of S, X of S, the equivalent signal flow graph for this one would look something like this. You have signal, system, signal, system, and signal. Okay, so you have, this is G of S, G1 of S, this is G2 of S, this is C of S, and this is X of S. This okay. Here, you don't do reduction, okay. The reduction is, you do reduction, but you don't do reduction in a way which we studied for block diagrams. We use a formula called or a rule called Mason's rule to do the reduction. We'll look at that Mason's rule, but this is the equivalent signal flow graph. If you look at the block diagram, this was a cascade block, right? You see this as a cascade block? Do you see 3 signals here? Why are there 3 signals? Do you understand why this is X of S or it's different? Right, you can look at that, or you can say when a signal goes through a system, it changes. Okay? So you have to identify that change. So anytime a signal goes through, so for example, if you have a really complex, so how many signals will you have here? Think about how many signals will you have here. 1, the signal here is different. Right? Because what is happening here? It's being added. Okay? So these 2 are 1, 2, 3. Now this is the same as this signal. If you had a block here, then there would be a 4th one, which is coming here. So you should be able to distinguish those signals. Okay? So this is the cascade form. And parallel form. This is important because in your signal flow graphs, see, if I did not identify this in the block diagram, it wouldn't make much of a difference. You would still inherently take this as a signal, right? You would reduce it in a way that your answer will not be incorrect. But if you ignore this, what would happen? This signal would vanish in signal flow graph. You have to be very careful when you do it to signal flow graphs. You see it? No, there is a different signal. But what I'm saying is, if you're looking at block diagram reduction, if you ignore that there is a different signal coming here, there is an X of S. If there is no X of S, you just assume or you put a value, you denote that signal by something else. Any variable. Got it? It is not 1. That's what I'm trying to say. Here it is 1. So this one, we'll come to that. Let's do the parallel first. So we have this block and this block. And say, so this is, we'll just do 2 of them. It should be fine. So G of S. Sorry, this is R of S. Okay. So how many signals do you have here? You have 4 signals. You see, R of S is 1 because the signal changes here. X1, X2, and then there is C of S. You see it? G1 is not a signal. G1 is a system. When a signal goes through a system, it doesn't remain the same. It changes its form, right? Does it change here? it change here? Does R of S change here? There's a pick-off point here, right? Discussed that last time. This is a pick-off point. The signal splits. This is a pick-off point. The signal does not change here. It just gets bifurcated.
But it does change before it gets to G.
Not before, after it goes through G1. Here the signal is still R of S. Here the signal is still R of S. But here it is not R of S, it changes. You cannot name it the same.
Okay, this was explained to that. I was thinking that maybe because it's when, I don't know, RFS changed there. Okay, I get it.
So you have this and so you have this is R of S. So this is here 1 and 1. You see it? This is when it starts getting complicated a little bit. R of S, right? Okay. It goes through system G1 of S. The signal changes to X1 of S. Now X1 of S and C of S. C of S is essentially X1 of S plus X2 of S, right? This signal just cannot go through. You cannot just add it there. So what you do is you create a system between signal which is just 1. You create a system between two signals saying, if I did this, if I had a 1 over there, would it change? It would not change anything.
Okay, so that one is basically just stating that for transfer function.
Yes. So there is a very defined formula or rule for something like this, which you can use to figure out the transfer function. So if you have a block diagram, just recall the block diagram we started with. What you do is, all you're required to do is represent it in the signal flow graph, and then you can apply that formula. You don't have to do the block diagram reduction yourself. You don't have to do the signal flow reduction. There is nothing called signal flow reduction. There's a formula called Mason's rule. You apply that Mason's rule or Mason's formula to get T of S. Exactly. Yes. Yes. So think about where would you start, right? As an engineer, how is this tool useful? So you're building system, okay? You're building a plant or a control system. So what you would do, you would take each component and assemble, correct? Each component will have something like this, right? Each block will have a G1, G of S, an input-output relationship, right? So you do the block diagram first in that, and then you use Mason's rule, or you use signal flow graphs to construct this representation. and then you apply Mason's rule to get the equivalent transfer function. Once you have the equivalent transfer function, what you have a system which you can analyze, which you can figure out how it works in a computational environment, right? You don't want to just build a system and say this is going to work. If you're asked to design something, you would do something like this. In the modern world, what you do, you simulate, right? You are not prototyping. You don't go from design to prototype. What do? You do design, you do analysis and simulation in a computational environment. So something like this will tell you that analysis and simulation will help you do that analysis and simulation. And once you do the analysis and simulation, you figure out if the system is meeting the performance characteristics, performance requirements. And then you go and do the prototype. So this, if you want to tune, you don't have to do the prototype, figure out what the performance characteristics are, change the design, then do the prototype again. You don't want to keep doing that, right? So this will help you do that. So the feedback form, the final form is something like this. So you have G of S, you have this, C of S, you have H of S, and R of S, okay, plus, minus. So how many signals do you have? This is X of S, right? This is E of S. So you have 1, 2, 3, 4, right? X of S, E of S, R of S, C of S. So what you start with is R of S. Okay. Between you have C of S. And this is 1, this is H of S, this is X of S. Actually, we'll have to put E of S. So this is R of S, this is E of S. And this is just 1. Okay. And you have to make sure you identify the signals or the signs, not the signals, but the signs. So here it is 1, here it has to be. So what happens if this was negative? You would have just made this as negative, minus 1. Okay. So that way it is C of S is still X1 or X2 minus X1. Yes. Here? Huh? It is negative, this is negative. So actually this is negative. So So x of s is negative 1, E of s is R of s negative minus x of s. Okay. So you see, this is your system. This is your system. And generally the norm is you use these arrows in between. Okay. It is just a practice, nothing more than that. So we'll look at Mason's rule in the next class and see if you are given such a system, how do you reduce it to a equivalent transform.